Today's speaker, who I hope you all know, is Kevin Cahill. Just a little bit about Kevin's history. So he got his PhD in physics from Harvard in 1967 under the supervision of Roy Glauber. And then he bounced around a lot of different places, it seems. So NIST, Wesleyan, Drew. And then he bounced around the south of Paris in the 70s at Saclay, the École Polytechnique, and the Orsay IPN. Had a couple more stops before landing at UNM in 1981. So he's been here for about 42 years. So Kevin is a theorist who has worked in several fields, including particle physics, quantum field theory, lattice gauge theory, and biophysics. And his textbook, Physical Mathematics, is now in its second edition. So after a long and impressive 42-year career at UNM, Kevin has finally decided to retire on January 1st and has kindly agreed to give this colloquium in association with his retirement. And he's not done thinking, as I think you can tell from his title. He's got a lot more to contribute, I think. So Kevin's going to tell us about simplicity and symmetry in physics.
Thank you for the introduction. So I picked the title for a reason, and I hope the reason will become clear during my talk. The basic idea is that theoretical physics is a mathematical implementation and development of simple ideas, guided, of course, by experiment. And some examples that I'll go over in today's talk are the uncertainty principle, local symmetry, the standard model, path integrals, and general relativity. Now, I'm not going to cover all of these in detail, obviously, but I hope to show how some simple ideas led to, and of course, many experiments in the case of the standard model led to these developments. Here's an outline. I'm going to talk about the uncertainty principle first, and then once again, talk about symmetry and simplicity, and then go on to gauge invariance, path integrals, and general coordinate invariance. I've prepared a lot of slides for today's lecture because I found that when I give talks, I prepare for a 50-minute talk and I finish in 20. And so I'm not sure if that'll be repeated today, but if so, it's a nice day, and that's probably be a good thing. So simple ideas lie beneath important concepts of physics. In the summer of 1963, I was on my way from college to graduate school, and I had an internship as a largely experimental intern at Brookhaven National Laboratory. In fact, they had me measuring the cooling properties of liquid hydrogen, and they were afraid that the liter of liquid hydrogen would explode, so they had me do this experiment in a field rather than in a building. And at that time, I was smoking cigarettes, and I found myself one afternoon walking toward the hydrogen with a cigarette, lit cigarette between my fingers. And then I realized what I was doing and I stopped. So that's why I'm actually here today. Anyway, at that during that summer at Brookhaven, Robert Oppenheimer gave a public talk. And what I remember from the talk, it was a very good talk, and what I remember was his description of the uncertainty principle. And it was, he pointed out that if you are using an instrument to measure the position of something, you have to know where your instrument is, because it doesn't do any good to say that the object is so far from the instrument if you don't know where the instrument is. On the other hand, one way of measuring momentum, the most natural way perhaps, is to let the object hit some light object and measure the recoil of an object of known mass that was just hanging in space and then was hit by the thing whose momentum you're trying to measure. And of course, that means then that the instrument, that is to say, the thing that gets struck by the particles whose momentum you're trying to measure, that has to be free to recoil. And so there's an intrinsic incompatibility between the two measurements. One has to be attached and the other one has to be free. And the result, of course, is that you can't simultaneously measure position and momentum of the same object. And the limit, of course, as you know, is Planck's constant divided by 4 pi. And this is a nice photograph that I got from somewhere on the web. This is Pauli, this is Fermi. I actually met Heisenberg once in Berkeley. I didn't want to take up much of his time, so I just said, hello, Professor Heisenberg. And he said,
You didn't say Weinberg.
yeah, it's good I didn't say Weinberg. I've said Weinberg so many times that I might have. Anyway, I just thought, since this is Planck's constant, that I'd mention something about Planck, Max Planck, and it's that his son, Erwin, in 1944, tried to assassinate Hitler. But unfortunately, on the one hand, he didn't succeed, and on the other hand, he was caught and he was killed by Hitler. So there was a lot of, there was some, sorry about that, there was some sadness in Max Planck's life. And of course, he foreshadowed, whoops, I'm sorry about that. He foreshadowed a great deal of quantum physics. H bar is in everything, all of quantum physics. You can use the uncertainty principle often to get results that, or to estimate quantum mechanical energy levels and other parameters. For example, you can take a wild guess by saying that RP is H bar, and then 1 over R is P over H bar, and then you substitute for R, you get this expression, you minimize it, and you get as the energy, the ground state energy of hydrogen. At least you get the exact answer to in the non-relativistic theory. Alpha, of course, being the fine structure constant, roughly 1 over 137. I'm told that it was Weishaupt who used this derivation in some of his lectures. In the basic uncertainty principle, of course, is that the position operator for one variable times the momentum operator minus the same things in the opposite order gives you H bar, and it gives you 0 if it's not, if both operators don't refer to the same system, and it gives you IH bar if they do. In quantum field theory, for scalar fields, if you have a bunch of scalar fields labeled by N and M, and dot is time derivative and dagger is the Hermitian conjugate, then this expression is what you get, is the generalization to quantum field theory of this uncertainty relation. For fermions, things are quite different. The minus sign becomes a plus sign and the I goes away. And of course, this gives you the Pauli exclusion principle. By the way, they were on a boat on Lake Como in northern Italy. That's where they were, where that photo was taken. You can use the uncertainty principle to say something about spin and to, in fact, derive an uncertainty relation for angle and angular momentum. It's that you look up here and you say, well, the uncertainty position is this, the uncertainty of momentum is that, and the uncertainty of position divided by the radius, well, that'll give you an uncertainty of angle. And so one just divides and multiplies by R. This is delta phi, and RP, of course, is angular momentum. And so this says delta phi, delta L is greater than or equal to h bar over 2. That tells us, of course, that spins, if they're not actually zero, are typically greater than or equal to h bar over 2. And for the elementary particles, that's what we find. They're all h bar over 2 and h bar or 2h bar for the graviton, except for the Higgs. And the Higgs is a weird field, really. One could say, who ordered the Higgs? I'm borrowing a phrase from a famous physicist whose name I've forgotten at the moment, but some of you may know. Anyway, these are the quarks in different colors and the leptons, and they all have spin 1/2, as you know. Here are the gauge bosons. The W minus and plus, the neutral Z particle. These are their masses in GeV, giga electron volts. This is the photon field. And then there are the massless gluons. There are 8 of them. And then there's the Higgs. That's such a strange particle. It's the only particle that spins 0. And it couples to everything, or almost everything, and it couples with wildly different coupling constants. And whoops, what did I do? It couples to the fermions and bosons with wildly different coupling constants, resulting in masses that are smaller than an electron volt and heavier than the mass of a substantial nucleus. So what I want to get to now is to say some things about simplicity and symmetry and the relation between them. Some of this I'm taking from some talks that we were very lucky to have given by Murray Gell-Mann maybe 10 years ago, maybe it's 20 years ago. After he retired from Caltech, he founded the Santa Fe Institute and gave a short talk on complexity, and I sat in on it, and whenever I could, I asked him a question, because when he answered questions, he sometimes went off on tangents, and he was so intelligent and had such a wealth of knowledge that his tangents were magical mystery tours, to use a hackneyed expression. Anyway, he was quite remarkable, and one of the things I learned from his talk was what complexity was, and the complexity of something is the length of its shortest description. That's an appropriate measure of complexity. And so, for example, the complexity of a circle is at most the length of an equation like this, x squared plus y squared equals r squared. Of course, there's more to it than that because we have to somehow say what we mean by x squared, y squared, and r squared, and plus and equals and square. But in any event, it's essentially that. On the other hand, the complexity of an arbitrary curve is at least twice the number of its pixels, and on a good screen, that's something, you know, way up in the millions. So this, why is the circle simpler? The circle is simpler because of symmetry. It has rotational symmetry, and that makes the circle simpler than just this squiggle that I drew. Another example is the complexity of a sphere. That's something like the length of this equation, and its symmetry is can be described, mathematicians describe it in terms of the group SO3, and physicists sometimes use SU2. On the other hand, a certain fruit called a rambutan has less symmetry and more complexity than a sphere. So that's, these examples illustrate that simplicity and symmetry are related. Symmetry, things that are really simple are typically symmetrical. Now, some of what I'm about to say to you sounded good to me, and I think there's some truth buried in it somewhere, but it's not mathematics, and I can't say that it's necessarily clear, but I think there's some truth to it, that the smallest things are the simplest and the most symmetrical because they just don't have room for complexity. And that means that elementary particles must be simple. They're the smallest objects we know of, and they're the simplest because they have no room for complexity, so they must be symmetrical. As I say, I think there's some truth to this, but as I say, it's not like the equations of mathematics or mathematical physics. Here are some of those equations, though. Symmetry leads to conservation laws, in particular in mechanics. Symmetry under rotations and translations in time and space lead to conservation of angular momentum, energy, and momentum. In field theory, if you have an action density or Lagrangian L that depends upon the space-time coordinates, these four coordinates, I use Roman indices because I'm not Greek, and most of the students aren't, most of the students aren't Greek, and so I think Greek letters are a little bit confusing. I actually was forced to study Greek in high school for 3 years, and though it's not that I have never seen Greek letters, but I think they're overused in physics. I once sent an email to Weinberg saying that his book had too many Greek letters. I didn't reply. So let's see, did I skip a slide? No. So if it only depends upon the coordinates, the four coordinates through the fields and their derivatives, then you can show using Lagrange's equations that the energy momentum tensor is conserved. And this, of course, is conservation of energy momentum in field theory. The simplest symmetries are what are called global symmetries, in that they change the fields the same way at every space-time point, independent. In other words, it's the same everywhere, the same transformation everywhere. So psi prime is e to the I q theta psi of x, and neither Q nor theta depends upon X. And so this is said to be global. This is the simpler kind of symmetry. And it's a symmetry, of course, that conserves charge. Curiously, one of the earliest symmetries, well, one of the early symmetries, the symmetry worked out in the 19th century, was a local symmetry. And it was Faraday and Maxwell who did that. I stole these. I assume he has a bar magnet there. I got these off the web somewhere. I don't remember where. Anyway, electrodynamics, of course, has gauge invariance, namely the electric and magnetic fields are the full curl of a vector potential. Notice this is anti-symmetric. Of course, you know curl is anti-symmetric. And they remain the same under a gauge transformation, even though this theta now depends upon X. So this is a local symmetry. And it's interesting that it was a symmetry of the 19th century. About the time of the American Civil War, this was understood. The change in the vector potential here depends upon the space-time point X, but the electric and magnetic fields remain the same. This is what we call local symmetry. So I'll often use the word local. I often use the word local to mean a symmetry that can be different at different points of space-time. So this is a local, the gauge invariance is a local symmetry of classical electrodynamics, and it foreshadowed the local symmetries of quantum field theory, which also require interactions. Now, I just said also, maybe I have the slides in the wrong order here. Anyway, this explains the also. If you have a local or space-time dependent transformation like this, so this is the gauge transformation of the vector potential. This is the charge symmetry transformation of a charged field psi. This transformation, even though the theta depends upon space-time X, it leaves unchanged this combination. This thing is often called the covariant derivative. And the reason is, if you work this out, substituting, replacing psi by psi prime and a by a prime, you find that the awkward terms cancel. The derivative acting on the theta in psi is canceled by the derivative that comes from the gauge transformation. And so this theory then is invariant, whereas if you didn't have A and you just had psi dagger partial derivative, space-time derivative, this means the partial derivative with respect to the kth component of this of space-time. If you just had psi dagger derivative, k derivative psi, the thing wouldn't be actually, the Lagrangian would not be invariant, but this one is because these two terms cancel. But this symmetry then has required the simple derivative be replaced by one that has this gauge field. And so now psi interacts with A, because the ordinary derivative has become this covariant derivative. And so this is the case for the quantum mechanics of charged particles, and it lies behind the solution of the hydrogen atom problem, for example. And so local symmetry or gauge symmetry is really amazing because it's a symmetry in which the angle can vary arbitrarily with the space-time point X. And this extraordinary degree of symmetry requires interactions. And that's really an important aspect of 20th century physics and 21st century physics. Now, Maxwell and Faraday were dealing with the symmetry of the circle, SO2 or U1. Yang and Mills generalized gauge invariance from U1 to SU2. They were thinking in terms of isotopic spin, and I think there was a lot of resistance to their paper and initially, but of course, the work they did is now regarded as an enormous step forward. Yang, by the way, is still alive. In fact, he's 101 years old. Last I checked, he was commuting between China and Stony Brook, but the last time I checked was a few years ago, so I'm not sure where he is now. Another local symmetry was developed and exploited by Weinberg, he who uses too many Greek letters, Glashow and Salam. They explained the electroweak interactions in terms of a product of two groups, a U1, so a circular symmetry, and then a symmetry of the sphere. So this is remarkably simple, really. We're talking about the symmetry of the circle, the symmetry of the sphere. They're the two most elementary symmetries, aren't they? Apart from just translation invariance. And what they came up with was a W here and a B, and one combination of the neutral W with B gives you the photon, and it turns out massless. An orthogonal combination gives you the Z0, which is also neutral, but much heavier, 91 GeV or so. Gelman and Zweig used SU3 for QCD. There, they said that the quarks came in three colors. Of course, we say color. Color is a mathematical color. It's not the actual color that you'd see if you could see the quarks. But the transformation looks like this. It's a 3x3 unitary matrix of Unix determinant, and it depends upon X, the space-time point. And so quantum chromodynamics, in order to have this local symmetry, the quarks have to interact with the gluons. And as we know, that leads to confinement, although exactly how that comes about is not very clear. So SU3 symmetry, like the SU2 cross U1 symmetry, requires an interaction. AI here is a linear combination of 8 3x3 Hermitian matrices, the matrices that generate SU3, each multiplied by a gluon field. So this is what the generalization of the vector potential is. So the important thing that I want to say here is that all the interactions of the standard model are those required by gauge invariance. I was hoping to get a laugh out of this, but it is to some extent a model, because in the Weinberg-Salam-Glashow theory, there's an L on the SU2, and that L means that the SU2 acts on the left-handed quarks and leptons, not the right-handed ones. And that means that the standard model is lopsided. And then we've got the great mystery of the Higgs. What about the Higgs? The Higgs interactions are gauge invariant, but what is the Higgs? Why is it there? Why does it couple to everything? In fact, apart from gravity, it's the only thing that couples to everything. And in fact, maybe it does have something to do with space-time and gravity, but I have no idea what. Here's an example of a Feynman diagram of a proton. Here a U quark turns into a D quark, it exchanges a W plus and a W minus with a D quark that turns into a U quark and back into a D quark. And then there are some gluons here, yellow-green gluons that allow this U quark to turn a blue U quark to turn green, then blue, and then green again. So that's just the actual temporal progress of a proton, of course, is just an infinite number of diagrams like this. But it's anyway, that was meant to be sort of an introduction to Feynman and path integrals. There's of course Feynman and of course Yang. Here's Feynman himself, and that grin is typical. I met Feynman at Caltech at a conference, and he actually gave me a lift to my motel. He's a very nice, he was a very nice man. In fact, if any of you are bored, some evening, you could go to YouTube and look for a video of his a lecture given by his sister, I think Joan Feynman, in which she described how she was his assistant and she was paid, I think, 4 cents an hour to be his assistant. And she would throw a switch on or off. And she describes how he once was holding a basket in which there were also papers on fire. He was holding them out the window. And at that time, their mother called Joan and said, "Joan, is Richard all right?" And Joan asked Richard, "Are you all right?" And he said, "Yes." And so Joan said, "Yes, mother, Richard's all right." Anyway, she told it better, so I recommend the video. Here's an example of the path integrals that he developed actually in his PhD thesis. And the idea is that if you have some system that goes from a start to a finish, the amplitude to go from the start to the finish is a sum of a bunch of amplitudes, and each of them is the action of the process times I divided by h bar. And so they're all unimodular phase factors, and you just add them all up. And so S1 is the action of process 1, S7 is the action of process 7. And that basically is the path integral. This phase factor that we see all the time in physics, including elementary physics, is the exponential of the classical action of a particle of mass m going from the origin to the point x, whether non-relativistically or relativistically. So if you write p dot x, it's the vector p dotted into the vector x minus et, and these terms cancel, and this is then the action and times t, and so it is is over h bar. The same thing relativistically, although it's more complicated relativistically. So in other words, the demos of optical interference in elementary physics are really demos of Feynman's path integral. The full scale path integral is a sum over all possible processes and or processes, I don't know which it is. Anyway, it's e to the I s of the action of the process divided by h bar, and you integrate over all processes. And of course, if you have a field theory with one field, and you have to integrate one real field, you have to integrate that real field at every point in space-time from minus infinity to plus infinity. So it's a totally bewildering, elaborate thing. On the other hand, from another point of view, it's something very, very simple. And the phase then of each contribution is the action divided by Planck's constant. And what you can see from this then is that a process is quantum mechanical if the action is small compared to h bar, because then you can't get a principle of least action out of this. Whereas if I think let's see, we have a backup pointer here somewhere. This must be it. We need to turn it on. Well, I can just talk while they're getting it ready. You see, if you can imagine many processes that are slightly different from each other, and if the change in the action is big, then these different processes. Okay, thank you. So, whoa. Going the wrong way. So, up here, if this varies a little bit, then these various phase factors will add together, whereas if the action varies a lot, then they'll cancel, and so the processes that are important, processes for which the action is big compared to h. Oh my goodness. Sorry. So if the process has, good gracious. If the process has an action big compared to h bar, then the processes that will happen are the ones for which the first order change in the action. This one works? Oh, great. Thank you. So classical physics is then described by the statement that the first order change in the action should vanish. And so that's illustrated in this slide here, where you have many different processes and the change in the action to first order is 0. Whereas here it's not 0. The process that goes from here to here is unlikely. The process that goes from there to there is likely. And all the equations of classical physics that I know of, or at least Lagrange's equations, come from the statements of the variation of the action should be 0 to first order. The path integral is, as I said, it's bewilderingly complex if you look at it in mathematical detail. On the other hand, it does give you a very nice picture of, as I just said, the laws of classical physics, and also certain other phenomena. And one of them is the Bohm-Aharonov effect. So if you consider a non-relativistic charged particle, moving in an electromagnetic field or with vector potential A, you can rewrite it this way. And if you forget about the part that's just mechanical, you then have the integral of A around a loop. And that gives you the magnetic field through the surface bounded by the loop. And that's illustrated here. You can have electrons coming through the two slits, and you can imagine this as being one electron goes this way and the other one just goes straight, or the difference in the action between the two paths is like an integral of A going around the loop. The idea is the magnetic field is here, only here, and then out here you have the vector potential being non-zero, and the vector potential actually is in the form of it points in like a circle. It's like a circle. So when this experiment was proposed and finally actually done, it established the reality of the vector potential in the minds of people who weren't sure of it previously. There's a picture of my thesis advisor, Roy Glauber, who won the Nobel Prize back in 2005. One of his early papers pointed out that the radiation from a classical current in the interaction picture, it's a time-ordered exponential of a space-time integral of the vector potential times the classical current, and this is, say, the vacuum state if you start just with a vacuum in the interaction picture. And apart from a phase factor that's typically ignorable, it's just an exponential of an imaginary linear combination of the electromagnetic field times a classical current. And that's a coherent state. And so this is so in other words, this was a 1951 paper of his, and the statement here is then that a classical current generates a coherent state. The formula he was writing on the board was for a coherent state that's an eigenstate of the annihilation operator, which in some units we can write as Q plus IP over 2H bar. And you can also generalize that to not Q, but W of Q plus IP. I forgot the 2H bar, but well, it said H bar equal to 1/2. Anyway, so you can have a B, you can have eigenstates of B, where B is this generalized annihilation operator. And if W is odd, and if it increases enough as Q gets large, then you can then an eigenstate with an arbitrary complex eigenvalue beta will exist, and this is a formula for it. And for beta equal to 0, it's the ground state of this Hamiltonian. The reason that sort of interests me is that you could write a Hamiltonian like this. This would be your sort of generic scalar field Hamiltonian. Except for the fact that I've written it in this funny way where there's a pi. The nice thing about this, though, is that it has a ground state of energy 0, and the wave function is a solution of this first order functional differential equation. Of course, functional differential equations aren't as easy as ordinary differential equations, so I can't solve that in general. When phi is quadratic, of course, it's just the vacuum of the free field theory. This way of thinking actually, I came upon it after studying supersymmetry, and in particular a paper of Witten's, in which long ago, 40 years or so ago, he pointed out that if you had a theory with exact supersymmetry, it would have energy zero. This side is completely speculative, and if there had been more white space, I would have put speculative as a warning. I think there may be some truth in it somewhere, but I can't really formulate it. The idea I have here is you have a red quark and an anti-red quark turning into two color singlet mesons, and I can imagine that minor changes of these trajectories amount to very much something like a gauge transformation, which doesn't change the action at all. So those amplitudes would add. On the other hand, if you have a red quark and an anti-red quark, I couldn't find any anti-red color, so I used blue, and here's some green gluons. The idea here is if you have small changes of these trajectories, they're not gauge transformations. They're not at all like gauge transformations. So the action, change in the action isn't necessarily small. So anyway, I don't know if this is nonsense or whether it could lead somewhere. So here's, goodness gracious. I guess I put so many slides that I am not ending in 20 minutes. Here are some Einstein quotes. He had many very clever things to say, as well as being perhaps the greatest physicist of modern times. He says, I never think of the future, it comes soon enough. Once we accept our limits, we go beyond them. Any fool can know, the point is to understand. Imagination is more important than knowledge. Two things are infinite, the universe and human stupidity. I'm not so sure about the universe. I never teach my pupils. I only provide the conditions in which they can learn. Everybody is a genius, but if you judge a fish by its ability to climb a tree, it will live its whole life believing that it is stupid. I know not with what weapons World War III will be fought, but World War IV will be fought with sticks and stones. The most beautiful thing we can experience is the mysterious. So notice he used Roman indices. Now, I think this is this is my memory of an Eddington quote, but I'm not sure of that. We have no way of knowing which system of coordinates is the true or best system of coordinates. So we should write the equations of physics in such a way that they are the same in all coordinate systems. And that is one of the concepts that led Einstein to general relativity, first to special and then to general relativity. This is Arthur Eddington, and he in 1919 led an expedition to observe the total eclipse. And these are some stars whose light was bent in accordance with general relativity. And he and two other British astronomers gave, I guess, the first experimental support to general relativity. I heard a story that he was once asked by a journalist. The journalist asked him, Sir Eddington, is it true that there are only 3 people who understand general relativity? And his reply was, who's the other one? Well, I don't know. I'm not good at telling jokes. I don't know what it is. Anyway, now I'm going to do a demo. And what you see here, well, why don't you guys read that and I'll turn the lights on and do the demo. So on his 76th birthday, one of Einstein's neighbors gave him a demo somewhat like this demo, which our physics department made. What we've got here, you see, was we're in a gravitational field and there's a spring here, but it's just not strong enough to pull the ball up and back in. If the ball is too heavy because we're in a gravitational field. But now if I put this up here, you see, when it's in free fall, it's weightless, gravity goes away, and the spring is strong enough. So I can do it again for you. I like this demo. Thank you. It's so simple and so anyway, he said, now I will let it drop, and according to the equivalence principle, there will be no gravitational force, so the spring will now be strong enough to bring the little ball into the plastic tube. This is an image I stole from Anthony Z's book, Einstein, Gravity in a Nutshell. Of course, Z's nutshell is this thick. He has a funny idea of nutshell. Now there's Planck finally with Einstein. And the idea here is that gravitational interactions are required by a space-time symmetry, namely that in order to have invariance under general coordinate transformations, you must have you must essentially have general relativity. And the gravitational interactions implied by general relativity are those required by the symmetry of, my battery has died again. The symmetry of, oh, here it is again. Well, the symmetry under general coordinate transformations. We can imagine that our space-time is a curved space-time in a higher dimensional flat Euclidean space-time with either one time dimension or two. Actually, you can typically get away with only one. If you imagine that the points of our four-dimensional space-time are p, but their derivatives then are tangent vectors tangent to our space-time, and so they're, in this case, five-dimensional vectors. You take the dot product according to the metric zeta or zeta prime, or whatever the metric is for the higher dimensional space-time, and it's all just minus one and then a bunch of pluses. What you get is the metric of space-time, where the metric of space-time is the dot product of these tangent vectors. In a flat, if you use the metric zeta, a flat 5x5 Euclidean space, the points look like this, and you use the previous formula, you get the metric, the Friedmann-Lemaitre, Robinson-Walker metric for a finite closed universe. If you use zeta prime, you get the metric for an open infinite universe. Turns out the Schwarzschild metric for a neutral static black hole can be embedded in a flat space-time of 6 dimensions, as can the metric of a charged static black hole. Every reasonable 3+1 dimensional manifold could be embedded in a flat space-time of 20 dimensions, and I think you only need one time. In empty space, particles fall along geodesics independently of masses. The equation is given by this, that the first order change in the action should vanish, and you plug it in and you get this geodesic equation. The Christoffel symbol here is, in terms of the metric, it's written this way. In terms of tangent vectors, it's written that way. And I can't resist saying this, the predictions of SU2 left cross U1Y cross the SU3 of the strong interactions and of general relativity have all been verified experimentally. On the other hand, supersymmetry implies that every particle of spin S has a superpartner of spin S plus or minus H bar. None have been observed. Of course, they could be lurking at higher energies, but supersymmetry strikes me as an extravagant symmetry. It's, as I said, it's not been observed. I really should, I was thought of replacing the battery, but I didn't. Where? Oh, here it is. I'm trying to get, that one's mine, and then the battery is dead. I should have, this one doesn't seem to work either. This may be the last slide though, apart from the references. Here, maybe I can do it manually over here. Can I do it manually?
Yeah.
Oh.
Because you manually and
Oh.
the pointer.
Oh no, I did it the wrong way. Whoa, what's happening? Jesus. Actually, it's curiously enough, the stuff that I left out was my own work, that I haven't gotten to, and I don't want to keep you here. Let's see. Yeah, so that's what I said about supersymmetry. The standard Dirac action is really awfully complicated. These C's are Cartan's tetrads, which are the tetrads with the ordinary 4x4 metric of flat space-time give you the metric of space-time. This is, I just think this is too complicated and ugly. So I proposed replacing the spin connection with gauge fields. Whether that works or not, I don't know. It has various advantages and disadvantages. The disadvantages are that it introduces a new vector boson and 6 gauge fields. The other hand, it treats local Lorentz invariants in the way local internal symmetries are treated. It adds, it makes the Dirac covariant derivative look nicer. And it also requires a massless, neutral, weakly interacting fields that would contribute to dark matter. So let me just end with Einstein's statement: the most beautiful thing we can experience is the mysterious. And luckily we have mysteries. For the last 20 years, we've had some really big ones. Dark or invisible matter is 84% of all matter. Dark energy is 68% of the energy of the universe. What are they? Why do we have the Higgs? Why does it couple so weirdly? Why are the electroweak interactions so lopsided? These are puzzles, and these are some references. And so I guess I'll go back a little bit and maybe go to the part where mystery. Yeah, I'll end here. So that's all I have to say. Sorry for going over by 9 minutes.